Okay, so my name is José Bento. I'm a student from Stanford University. My advisor is Andrea Montanari. So this work has to do with learning graphical models. So the problem we're interested in here is understanding, for the case of an easy model, we want to understand which graphs can be easily learned or not. Okay, so easy model basically is a probability distribution over a graph in which for each edge present there's a term of the sort e to the theta x1, x2. Okay, and given a lot of independent samples or a certain number of independent samples, we are interested in understanding whether a given algorithm can or cannot learn the underlying graph. So different graphs give origin to different distributions. We observe samples from this distribution, then we want to recover the underlying graph G. And so there's results in the literature that gives us conditions under which different algorithms are or not able to recover the underlying graph. But in general, the conditions, if we read the papers, the conditions under which we have success or failure are expressed in very different ways, and it does not become easy to understand if for a specific family of graphs these conditions hold or don't hold, okay? Or even to do a comparative analysis of these theorems, okay? So the main contribution of our work was to analyze 3 different kind of algorithms and show that for all these algorithms there exists a single condition, a single criteria under which there's success recovery or not, okay? And so the condition roughly tells us that if the strength of the edges is greater than a constant over the maximum degree of the graph, then all of these algorithms will either fail, okay, or will require a running time that is too large. Okay? And if the connection strength is smaller than some other constant divided by the maximum degree of the graph, then all these algorithms will work in polynomial time with a constant degree in exponents, and will require a number of samples that is logarithmic in the number of nodes in the graph. Okay? And so the first algorithm that we analyze, the simple thresholding algorithm, where we have said that the edge is present or not if the empirical correlation is above or below a certain value. So the second algorithm is an algorithm by Bresler, Mossel, and Sly that tries to recover the graph by learning each neighborhood of every node. And in this case, the way we try to guess the neighborhood is by making use of this conditional independence property of pairwise Markov random fields. So in this case, we know that if we condition on the true neighborhood of a node, then the distribution of that node conditioned on the values of this neighborhood is independent of everything else. So making use of that property, one can, by testing several potential neighborhoods, one can eventually guess the right neighborhood of the graph. And the third algorithm that we analyzed was an algorithm by Ravi Kumar and Martin Wainwright and Lafferty, and basically consists in solving some regularized pseudo-likelihood method. Okay. And again, so the idea is the same. So all these algorithms, although they are distinct, they all work or fail roughly under the same regime of theta being greater than 1 over delta or smaller than 1 over delta. So these are just some simulations to exemplify these results for this particular algorithm. So here we see the probability of successful reconstruction of a regular graph of degree 4 as a function of the temperature, as a function of the link strength. And as we can see, as the link strength becomes greater than the critical temperature, then reconstruction stops being possible. Okay? Here we are talking about exact reconstruction. So all of these concerns exact reconstruction. Okay? And finally, I mean, for the particular case of this algorithm, we know that the success of this algorithm is related to this thing called incoherence condition, and one can actually compute this incoherence condition for random regular graphs with high probability, and we can actually see that the incoherence condition will actually be violated again at this critical temperature, which kind of coincides with the numerical results. And that's it. Thank you.